SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon to all. I am Dr. V.O. Thomas, Associate Professor in the Department of Mathematics, Faculty of Science, the Maharaja Sayaji Rao University of Baroda. Today I shall talk on applications of differential equations. Probably differential equation is one of the most applied branches of mathematics. Its applications take different fields in our day-to-day life. We just start with the definitions of differential equation. As you know, differential equation is an equation containing derivatives of one or more dependent variables with respect to a single independent variable. This is usually called ordinary differential equation. Now, when you talk about the differential equation, you have to think of the order and degree of this differential equation. For example, I have given two examples. dy by dx plus 5xy is equal to e raised to x. d square y by dx square plus 2x into dy by dx minus 6y is equal to 0. If you look to the first equation, it is a first order equation because the order of the derivative is 1. If you take the second equation, the order of the derivative is 2, highest order is 2, so it is a second order equation. Now, whenever you have a differential equation, your immediate interest is to find out what is the solution of the differential equation. That means what function will satisfy the equation identically. So, a solution of a differential equation means any function phi defined on some interval which when substituted into the differential equation reduces the equation to an identity. Then such a function is said to be a solution of the differential equation on the interval I. Look, for example, a function phi of x is given x raised to 4 by 16. And this function is a solution of the differential equation dy by dx is equal to x into square root of y. And this solution is defined on the interval minus infinity to plus infinity. Why it is called a solution? Because when you take y is equal to phi of x, that is equal to x raised to 4 by 16, and you substitute in the differential equation, both sides will become equal, it will become an identity. So that one can easily check it. Now, when you talk about the solution of differential equations, solutions satisfying certain conditions are also important. Usually we call them as initial value problem, IVP. What is an IVP? The problem solve the first order differential equation dy by dx is equal to f of xy subjected to this condition, that is y at x naught is equal to y naught, that is called a first order IVP. So you are given a first order equation and you are given a condition and based on that condition you find out the solution. Now if the problem is solve second order differential equation d square y by dx square equal to f of x y y dash subject to y at x naught is equal to y naught, y dash at x naught is equal to y1, then that is a second order IVP, because two conditions in this case are needed. Now actually what you are doing is that you find out a solution which is passing through a given point. Then people are interested in finding out not only general solution, but people are more interested in finding out unique solution. What do you mean by unique solution? When there is precisely one solution passing through a point, then we say that we have a unique solution. So through the point x naught, y naught, if more solutions are passing, then it cannot be a unique solution. There are different types of first order equation. When you talk about first order equation, there are different types. And in one type, that is called linear first order differential equation, that is very important. In many applications, many physical situations, you can translate it into a first order linear differential equation. A differential equation of the form dy by dx plus px y equal to q of x. This is a general form of a linear first order equation, where p and q, they are functions of x alone. Getting solution in this case is easy. What you are looking is, you write what is the integrating factor. Integrating factors are functions which facilitate the integration of the differential equation. So for our differential equation, linear differential equation, e raised to integral p dx is an integrating factor. So if you multiply the equation throughout by e raised to integral p dx, the equation becomes integrable, and you can write the solution in the form y of x is equal to e raised to minus integral p dx into dx multiplied by integral q e raised to integral p x dx plus c, it is a constant of integration, then e raised to minus integral p dx. As I told you that many physical problems can be reduced to first order equation of this form. Now we shall discuss in detail some of the problems which we can convert it into first order linear differential equations. One is population model. You can make a mathematical model of the population growth, then that will go towards a first order differential equation. Second point I am going to discuss is radioactive carbon dating. The third application, you can apply first order differential equation in the study of compound interest. Then we can use it for mixture problems. Newton's law of cooling you can express in terms of a first order differential equation. And a one dimensional heat flow can also be represented in the form of a differential equation. There are many other problems which you can, actually physical problems which you can convert into first order equations. But I shall discuss about these 6 somewhat in detail. Let me take the population model. Let us assume that P of t denotes either the population of a country at time t, or P of t represents the number of bacteria in a laboratory experiment, or it can be P of t can be the population of insect attacking a crop in a field. In all these 3 situations, you can consider dP by dt as the rate of change of the population with respect to time. How the population changes with respect to time. That is what dP by dt represents. The derivative dP by dt, that is measured in units of number per unit time, because rate of change of P with respect to time. Now the growth rate is represented by 1 by P dP by dt, that is the rate of change of P with respect to time you divide with the population, total population. Now if the rate of growth, that is a constant, you can write it in the form 1 by P dP by dt is equal to K, or you can write dP by dt is equal to K into P. So you can see that this is a first order equation. This is a variable separable equation also. So if you solve it, that is, you can write this as dP upon P is equal to K dt. Then you integrate it. So when you integrate it, you will get the solution P of t is equal to C e raised to kt. Here C is the constant of integration. Now you cannot say anything about the population in a later time unless you know what is the constant C. So to find out that constant C, we use what is called initial condition. That is, you are assuming that when time t is equal to 0, initially the population is P of 0. P of 0 means that is the initial population. And suppose you put t is equal to 0 in the equation P of t is equal to C e raised to kt. E raised to kt will become e raised to 0, and you will get C is equal to P of 0. So the constant is determined. The constant is nothing but the initial population. Now suppose if you want to draw the graph of this, P of t is equal to P naught e raised to kt, you take time along the horizontal axis and Pt along the vertical axis. Then when time t is equal to 0, you have P of 0. When time t is equal to 0, you have P of 0. You can see that point there in the graph. Then after that, if k is a positive constant, k is greater than 0, as time increases, P of t also increases, the population increases, and the graph is shown in the figure. Now take the situation in which k is less than 0. So when k is less than 0, what happens is that P of t go on decreasing, and when t goes to infinity, P of t will go to 0. So from the graph you can see that. So it will go to, when t goes to infinity, P of t goes to 0. So this is the first model, population model, how you can convert into a first order differential equation, and then you can solve it and find out the population at a later time by using that formula. Now another application of first order equation is radiocarbon dating. In 1950, the chemist Willard Libby devised a method of using radioactive carbon as a means of determining the approximate age of fossils. And actually for this he got Nobel Prize for chemistry in 1960. The method is this: the ratio of radioactive carbon represented by 6C14 and ordinary carbon 6C12, that is a constant. In the living organism also, this ratio will be a constant. Now what happens when the organism dies? The absorption of this radioactive carbon through breathing and eating, that terminates. Hence one can estimate the age of the fossil by comparing the carbon ratio in the fossil with that in the atmosphere. We take the half-life period of carbon, radioactive carbon, about 5600 years. And with the help of this law of radioactive decay,